Okay. So let's get started. Okay. So yesterday we were at this point. We have discussed what we mean by predicate. A predicate or a prepositional function is a statement which involves a single variable or multiple variables. That predicate becomes a preposition whenever you are putting a value for variable inside a predicate. For example, if we observe the statement p of x denoted as 2x is an even integer, if I put here instead of x any value of integer likewise 1 2 3 and so on, we will get the exact integer and we can determine the truth value of this. Obviously the truth value after putting any value of x will be true because it is multiplied by 2. So if we are multiplying any number by 2, the resulting number will always be an even integer and the truth value for this p of x will be 2. So we are assuming the values for this x using two methods. One is method of direct substitution where we are directly putting out the values, or the second method is quantification method where we are writing English statement using the words for all. We are taking all values from the given set, or we are assuming some values, at least one value from the given set. Based on that, we are having two types of methods. One is a direct substitution and other one is quantification method. Okay. So yesterday I was discussing that the set from which we are taking the values for putting out into a predicate, that set is known as a domain. It is also known as universe of discourse. So for this example, we would have set of integers as the domain or universe of discourse. This I have already discussed. Okay. Quantification. Now, instead of direct substitution, if I have to assume the values from certain range of values, I can make use of either for every, also known as for all, or for some. These are the two types of quantifiers. So how we are denoting for every or for all? We will make use of this symbol for denoting for all. What is the meaning of for all? For all values from a given domain, the given predicate will be true. That is the meaning of for all. We need to take every value from the given domain or universe of discourse. And meaning of for some, the meaning of for some will be, you will be using the symbol. The symbol is reverse E. Okay. There exists at least one value for which a given predicate or prepositional function will be true. You could observe an example. I can clearly see that for every triangle T, the sum of angles of T is 180 degrees. We have any triangle existing in the world in the geometry where the sum of angles of that triangle is not 180 degrees. We hardly see any triangle because we know that from geometry, every triangle we are going to have sum of angles of the triangle exactly equal with 180 degrees. So I can say that here there will be use of quantifier for all. So how can we read this? We will read this as for all triangles, the sum of angles of that particular T is 180 degrees. It is applicable for all. Okay. But you can observe the second example. Can I say the same for the second? Let us check. For every integer n is less than p for some prime number p. Okay. It may not be the case for negatives. Okay, we are not considering here negative integer. We are concerned about the positive integers. For every positive integer n, the value of n is less than p for some prime number. See here, for some prime number is given. So if I consider an example like suppose we are having list of integers starting from 1 to infinity, and there are primes like 2, 3, then 5, 7, 11, and so on. And if we are randomly picking a number from set of integers, let us say I am picking up a number 3 from set of integers. 3 will hold a value of n. Okay, n is 3, let us say. So what is given for every integer n? Okay, let us say n is 3. N will be less than p for some prime number. Are there prime numbers which are greater than 3? Obviously, yes. There are many prime numbers which are having higher value than 3. So certainly we can say that this statement can also be represented using for all quantifier for every integer n. You can take any example 1. Whether 1 is less than any other prime number? Certainly yes. 1 is less than 2, 1 is less than 3, 1 is less than 5. It is given that at least 1 for some prime number that n will be less. How come? If I am taking some larger value of n, let us say I am taking a larger value of n as 255. Okay, so 255. Okay. If 255 is the value of n, whether that 255 is lesser than some higher prime number? Obviously, yes, this 255 will be lesser than some higher prime number. So here we are again using for. So what is the symbolic notation for this for all? You are going to use this symbol. You have seen this many times while learning mathematical axioms or theorems for all. So this for all quantifier is known as universal quantifier, that I have discussed in yesterday's class as well. Universal. Why universal? Because it is assuming everything in the given set. One can write p of x. P of x is our predicate for every x in a domain D in the set of assumed values using the symbol for x p of x. Are you ready? This symbol is called the universal quantifier. How to write the predicate in terms of universal quantification for all x p of x. Moving further, how to decide truthness of a predicate using this for all quantifier. So you can observe this statement: for all x p of x is true if predicate p of x is true for every x belonging to domain assumed for that predicate. It will be false if p of x is not true. If p of x is false for some value x belonging to D. Example, let p of n be a predicate. Do not get confused with the word prepositional function. This is also known as a predicate. What is a predicate? A statement involving usage of variables. So let p of n be a predicate such as n square plus 2n is an odd integer. This is a predicate. N square plus 2n is an odd integer. Okay, so what will be the domain from where to assume the values for the small n? I'm going to assume the values for small n from set of all integers. Okay. We could assume that we cannot say that for all values of small n belonging to D, which is set of integers, this p of n will be true. Okay. If you are still confused, let me say this is D. Okay, I am writing over here. I hope this is visible. This D is equivalent with, we have to put the values for small n from this set 1, 2, 3, and so on. Okay, up to infinity. So this is my set. From this, I am going to pick one value randomly, and I would be happy to say for all values of x, p of x is true if for replacing this value of small n by every value, we are going to get this statement as a true. So do we get this? Let us check one by one. So this is my predicate. Let us put value 1. So 1 square plus 2 into 1, that is 1 plus 2, 3. 3 is an odd integer, perfectly fine. If I put 2, what is the square of 2? 4. 4 plus 2 2s are 4. 4 plus 4 is 8. 8 is not an odd integer. That means Pn, predicate P of n, is true only when n is an odd integer. Let us try for 3. What is 3 square? 9. Plus 3 2s are 6. 9 plus 6 is 15. So we could observe that P of n will be true only when n is an odd integer, while it will be false if n is an even integer. This is our conclusion for the given example. Are you getting? So this for all x p of x is true is not holding true in this case. Okay, it is certainly false. Okay, moving further, the second, up to this point, whether it is clear? Can you reply in the chat window? Is there any lag in the audio, video, streaming, anything from your side, your end? Whether it is fine? Shall I go ahead? Yes, clear. Okay. Because you are going to solve the examples, okay? You find it easier whenever I am discussing, but whenever I am asking you about the examples, the things become difficult. Okay. Existential quantifier. What is the meaning of existential quantifier? For some value of x belonging to domain, predicate p of x is true. If there exists an element x in the domain D for which p of x is true. It may not be the case that for all values the predicate is true, but it will be the case that for at least one value of x, the given predicate p of x is true. We are going to use the symbol reverse E for denoting existential quantifier. Read as there exists. Okay, there exists. This is existential quantifier. Moving further. So, okay. The universal statement for all x p of x is false if there exists a D such that p of x is false. I mean to say, you can assume this as a counter example. Okay, what is the example? So can we say that this, can I write like this, for all n, okay, as this is a mathematical subject, okay, I am using annotations on the slide using my mouse, so it may not be perfectly fine while I am writing on this. Okay, so what is this meaning? For all n, p of n is true. So do we have that? Can we say p of n predicate is true for all values of n here? Can I say? I cannot, because I have shown you an example. P of n is true only for odd integers, but it is false for even integers. So we cannot say for all values of n, P of n is true. Okay, but can we say like this? There exists a value of n. From where to take a value of n? From set of integers. There exists a value of n for which P of n is. I hope you are getting the things. Okay. If you are still not getting, I will explain with the help of notepad. Okay. This statement P of n denoting n square plus 2n is an odd integer. It's false for universal quantifier for all, because not for all values of n P of n is true, but this statement is true for there exists a value of n, at least one value of n for which P of n is true. Is it fine? Is it fine? I used to ask you repeatedly. So what is the counter example? So if we are failed to state that universal quantifier is true for all values, if we are getting that universal statement for all x, P of x is false, then obviously there would exist at least one x for which we could perhaps get P of x as true. I am saying as true. Okay. Just observe the example. The value x that makes P of x false is called a counter example to the statement for all x, P of x. Good. So if we are reading only this statement for all x, P of x, meaning of this statement is for all values of x, P of x is true. If we are getting for all values of x, P of x as false, that means we need to identify some value of x from D such that predicate is false. So in this example, I have identified the values of n, one value as 2, for which I am getting this as a false. So this is known as counter example. You can check out with the help of this. Let P of x be a predicate stating every x is a prime number for all integers x. It is certainly false. I know that all integers are not prime. So how can I take the counter example of this? If x is 4, an integer, this x is not a prime number. So there exists x for which x is not a prime number. So what is our counter example? 4 is a counter example to p of x being 4. Are you ready? Our predicate p of x was every x is a prime number. First of all, let us check the truthness of this. Let us put 1 is a prime number. Okay. 2 is a prime number. 3 is a prime number. If I put over here 4, okay, I could observe that I am having factors of 4 as 2 and 2 other than 1. So 4 is not a prime number. So if x equal to 4, this x is not a prime number. 4 acts as a counter example for making that for all as a false. See, things are going a little bit complicated, I could say. Okay, so if there is anything which is not clear, please feel free to ask me in the chat window, or if I am not seeing in this meet window, always you are supposed to unmute your mic, stop me at that point so that I can reiterate whatever is not clear. Is it fine? If something is not clear. Okay. So moving further to this, before going for these laws, okay, let me clear these laws as well, and otherwise afterwards I will come back to the example. So can we apply the De Morgan's laws of logic for this for all and existential quantifiers? So we can certainly apply the De Morgan's laws for logic here. So observe that if p of x is a prepositional function or a predicate, then each pair of prepositions in this have the same truth values. I could have negation. So what is the meaning of this? How to read this? How to read this? What is the negation of for all x p of x? It is not the case that for all values of x, p of x is true. What is the alternative meaning of this? There exists at least one value of x for which p of x is not true. You can read out this. What is the meaning of A? How to read A? It is not true that for every x, p of x holds. Holds means true. Holds means true. Is equivalent to saying there exists at least one value of x for which p of x is not true. So here we have used De Morgan's law. I am applying negation to a bracket. So this for all becomes there exists. Okay, for all will be replaced by there exists, and individual predicate will be replaced by negation of predicate. Remember, while applying negation, we are replacing for all by there exists and there exists by for all, vice versa. So you can check the second statement. What is the negation of existential quantifier? Negation of there exists x, p of x would be for all x, negation of p. You would get confused with this. Okay. So what is the how to read this? It is not true that there exists x, at least one x, for which p of x is true. Is equivalent to saying that for all x, p of x is not true. I am going to take the example so that your things will be more clear, but I am showing you a notation of using De Morgan's law in this context of quantifiers. So what is the negation of there exists x, p of x? Its negation will be, if we are taking this negation inside, this there exists will become for all. So for all x, you are applying negation to individual predicate. It is not true that there exists an x for which p of x is true. Will be similar to saying for all x, p of x is wrong. I know that you are confused with this. So, so let me show you a sample example. The same example that we are been discussing throughout. So we know that this p of n is n square plus 2n is an odd integer. We come to know that this is not true. This is not true means what? there exists at least one integer for which this is true. So if I ask you what will be negation of this, what will be negation of this? Negation of for all n p of n will be there exists n for which negation of p of n. You will ask me, sir, how you are going to prove this? So that is the reason why I have taken you to this slide. Okay, I'm going to prove this. So just observe. So this is what for all values of n, n square plus 2n is an odd integer. That is our original statement. What is its negation? There exists at least one value of integer for which this statement is false. And I have shown you there are a couple of values like 2, 4, 6, 8, 10 and so on, for which this statement is false. Okay, which statement is false? This one is false. I think this is making a sense. Whether it is making a sense or it is somewhat difficult. Only 57 I could see on a board. Okay. So, the remaining have gone. This should not happen. Only 57 I am observing. Does it make a sense? It is making a sense. Okay. Okay. If it is making a sense, then why the people are leaving the meeting? I'm observing only 57 on board. I'm having a habit of taking attendance in between. Do not rely on your final attendance or the first attendance as such, anywhere. These are the laws of logic. So summary is what? In order to prove that universally quantified statement for all x, p of x is true, it is not enough to show p of x is true for some value x belonging to D. You must show p of x is true for every x belonging to D. Are you ready? In order to prove universally quantified statement for all x, p of x is true, you need to prove that p of x by putting out every value of x, and only then you can say that that will be true. Otherwise, for proving this as a false, we need to look for the counter examples. So in order to prove the universally quantified statement for all x, p of x is false, it is enough to exhibit. We need to just find, okay, if I want to show this as a false, I need to find certain case, some x belonging to D, for which p of x will be false. So this x is called as a counter example to the statement for all x, p of x. Couple of examples that I do have for you. I am going to discuss. Okay, so do not worry. I am not going to give you anything to you to solve. Okay. Unless and until this is clear from my side, I will not discuss. I will not expect anything from yours. So quantifiers are the symbols used with prepositional functions. Universal quantifier, this representation, existential, read as there exists at least. So if any set of all positive numbers for all x belong to n, x plus 3 greater than 2, it is perfectly fine. You can put any value of x from given set of integers. You would observe that every time this statement is going to be true. Thus, we can say that this for all quantifier can be used for the first statement, x plus 3 greater than 2. But the same thing is not applicable for this. If I am observing this predicate x plus 2 less than 7, certainly there are some values of x for which this statement will be false. Hence, we cannot apply here for all operator. So we are saying there exists a value of x belonging to n for which x plus 2 less than 7 is true. Are you getting? Here we cannot apply for all. You cannot apply for all for the second step. So if this is clear, now they are not going to give you examples in the form of mathematical operations. Okay, sometimes the examples may be in the form of English like statements. So consider the statement, all cities are clean. What will be its negation? Negation of this all cities are clean will be, it can be written in two ways. You could say it is not the case that all cities are clean, or you will say that there exists at least one city which is not clean. This is the application of De Morgan's law, which we have seen recently. This is, I can represent the statement like this: for all x, okay, let us say p of x, okay. Do observe whatever I am writing on the slide, do not go through the text which is present on the slide. If you are going through the text, you will not understand anything that I know. So how we are writing? All cities are clean. Let x denote all cities in the world. Okay. For all x, if those are the cities, let p of x denote a predicate which says that cities are clean. For all cities, they are clean. So I am writing in symbolic representation. Okay. What will be its negation? What will be its negation? We are having De Morgan's law. So negation of for all x, p of x is there exists x, negation of p of x. Are you getting? What is its negation? Negation of this statement will be there exists x, sorry, negation will be there exists x, negation of p of x. I hope this is clear. Okay. So how can we write negation? The first way of writing in statement format is, it is not the case that all cities are clean. This is perfectly fine. Or alternatively, I can write there exists at least one city which is not clean. So that is what I mentioned here. There exists a x. X is what? City. There exists a city, at least one city. Negation of p of x. What was p of x? Cities are clean. So negation is city is not clean. That is the second. There exists at least one city which is not. Is it fine? It should be fine. Symbolically, we can write negation of for all x m. M is a set of cities. Okay. They are saying m is set of cities. For all x belonging to m, x is clean. If we are saying, and I want its negation will be there exists x belonging to m such that x is not clean. This is what I have discussed already. Now things will be more clear. Okay. Where m is set up. So according to De Morgan, negation of for all x belonging to a, p of x is equivalent to saying there exists x belonging to a such that negation of p of x, and vice versa. So what to remember? We need to replace for all by there exists. We need to replace original predicate by its negation and vice versa. So moving further, predicates. Okay. We can have predicate comprising of single variable, two variable, three variable, four variables, or n variables as such. A prepositional function or a predicate with more than one variables can be written as p of x1, x2 up to x of n over a product set of, forget about this product set for a while. I'm going to show you about product set shortly. So if we are having only one variable like this, I'm writing here. Okay. If I'm saying I'm having p of x, this is known as one place predicate, only one variable. If we are having p of a, comma b, comma c, this will be known as three place predicate. If we are having n such variables inside a predicate, we will treat that as an n place predicate. Okay. So observe here an example. Let a be a domain having only four integers 1 to 4, and we are having predicate comprising of x comma y denoted as x plus y equal to 5. So we can say that for this condition we would have a true statement stating for all x there exists y p of x comma y. From where to take the values of x and y? I am going to take the values of x and y from this given set. The set is given here. In earlier examples, we have been given a set as set of all integers. Now we are specific. Values have been given. So let us say I am putting a value of x as 1 and I will put the value of y as 4. So 1 plus 4, 5. If I put value of x as 2, I need to put value of y as 3. Then if I put value of x as 3, I need to put value of y as 4. If I'm putting value of x as 4, I need to assume value of y as 1. in order to have this result as true. Getting? So what is mentioned here? So if we want to write a true statement for this p of x denoting x plus y equal to 5, we can write it as for all values of x, there is at least one value of y for which p of x comma y is true. Are you getting my point? I hope you are getting. Okay. For every value of x from this domain A, I have at least one value for y which satisfies this equation. I have shown you the example. For 1, we are having value as 4. For 2, we are having value as 3. For 3, we are having value as 2. For 4, we are having value as 1. Just a moment. Just a moment. Hold on. Actually, my laptop got discharged, so I have put it for charging, nothing else. Okay. So you could observe here, we can certainly say that for all values of x, there is at least one value of y for which p of x comma y is true. Okay. But if we change the order of this quantifier, if I'm saying there exists a y for x, p of x comma y, whether this will change the meaning of entire statement? Yes, it is going to change. Just observe what I'm saying. If we write for all, sorry, there exists a y, I'm writing there exists y first, and thereafter I'm writing for all x, p of x, y. The meaning of the statement becomes there exists a y such that for all x, we have x plus y equal to 5. Do we have any such y existing here? Meaning is there exists a y. Okay, there is at least one y. There exists a y, a single y for all values of x, such that we are having x plus y equal to 5. Certainly, this is not the case if we are taking 1. Okay, can we say 1 plus 1 equal to 2? No, it is not equal to 5. If I take y as for 2, certainly not 4. No. The meaning is changing if we are writing there exists before for all. We are going to solve many examples based on this. Today is an overview about how to make use of quantifiers. When we negate statements with more than one variable, each for all will be replaced by there exist, and each there exist will be changed to for. So negation of for all x there exists y, for all z p of x comma y comma z will be there exists x. I'm changing for all to there exists x, for all y there exists z. Negation of this. Okay, be concerned about this. Here we are having for all, so it is replaced by there exists. Here I am having there exists, so it is replaced by for all. Here I am having for all, so that is replaced by there exists. And again we are applying negation for this predicate. So negation of p x comma y comma z. Fine. Anything to say in the chat box? Anything to discuss in the chat box? Certainly, if it is, let me know. Okay. Anything perhaps that you want to discuss? See, I'm observing that somebody joining now. Okay. You should be present at the starting of the lecture only. So, one question, just for practice. You have to answer in current class only. I'm going to tell you how to use these quantifiers and everything after solving this example. So you are seeing in front of you the predicate statement. Every teacher is liked by some student. And the question is how to represent the statement in terms of quantifiers and the symbols. So again, just to make you clear, teacher X is a predicate denoting that X is a teacher. Student Y is a predicate which denotes that Y is a student. Likes is a two-place predicate which denotes that Y student likes teacher X. I think I am clear with the notations. Okay, now you will be telling me out of these four options, which is correctly denoting the statement, every teacher is liked by some student in the chat box. See, every means I will be using for all, that is for sure. Okay. Is liked by some. If there is some, I have to use there exists. I have given you hint as well. So now can you tell me the answer? Can you give me the answer in the chat box about this particular example? I said that teacher X denote that X is a teacher, student Y denote that Y is a student, and likes Y comma X is denoting that Y is liking X. Take your time. Okay, I think I should minimize this. It will also be available. All are present physically. Hello. 1, 2, 3. Mic test. Hello. All are present physically as well as mentally prepared for attending this lecture. If so, yes. Okay. If so, can you just give a try? Okay. Can you just give a try? I am not asking you for perfect answer. It may not be possible for you to get a perfect answer unless until I have discussed the terminology. But I am asking you based on your understanding. Okay. B. Okay. B. You are saying B. So let's try to interpret each and everything one by one. Okay. So what will be meaning of this? For all X, let's say X are all for all X. Okay, X is belonging to teacher. For all teachers, if X is a teacher, then there exists a Y, such that Y is a student and he likes a teacher X. That is the meaning of this first statement, option A. What is the meaning of option B? For all teachers, there exists a student. Okay, there exists a student Y, such that Y is a student and he likes teacher X. Okay, this is saying that there exists a student Y for all teachers. That means a single student is liking all teachers. This is wrong. How a single teacher can like all all teachers? Obviously, a single student can like all teachers, but as per the given statement, every teacher is liked by some student. It is given, no? And this is controversial with the given statement. It is saying that there exists only one student, a student, which is liking all the teachers. So we will not consider this C option. Okay, let us go for D. For all X, for all teachers, there exists a student, and the student likes here and here there is the usage of conditional. Okay. And there exists a Y, such that student Y likes teacher X. So I have received the responses which are saying A, some are saying B, some are saying okay. Now see, while deciding when to use conjunction, when to use this conditional, it is all a matter of our reasoning. It is all a matter of our thinking, our understanding of English statements. When to use this conjunction and conditional is very, very crucial to know. Okay. Otherwise, it will change the entire meaning of your statement. So observe the solution in front of you. The statement given, we can write the given statement like this: for all X, if X is a teacher, then there exists a student Y who loves X, who likes X. Okay. Which can also be represented using the quantifiers as follow: for all X. Okay, for all X, if X is a teacher, teacher of X, then there exists a student Y. There exists a student Y, and okay, and that particular student likes X. It is important to note that implication is almost used in conjunction with the quantifier for all. So whenever there is a usage of for all, we are going to use this conditional. Are you getting my point? X has to be a teacher for getting liked by a student. So that is the reason why we are using conditional. So when to use conditional? In case of for all. And if there is a quantifier there exists, we will be making use of conjunction. This is wrong. Okay, this is wrong. My mistake. So we will be using conjunction if there is usage of there exists. So our option number B will be correct. Are you getting? आता बऱ्याच जणांना ओके आय एम अगेन टॉकिंग इन मराठी सॉरी many of you may have a problem that why not this and why this for liking a teacher X Y has to be student. Is it fine? What is the meaning of this? There is a Y. If Y is a student, then that Y is liking X. And what is the meaning of this? Y is a student at the same time that Y is liking X. This is more meaningful in comparison with whether it is clear. Does it make a sense why the option B is correct and why not A? I will have a couple of more examples afterwards so that you will have a clear understanding when to use that conditional and when to use that conjunction while using for all and there exists. Okay, so let us conclude our lecture for today. Okay, I know that this is the fourth lecture and this is the only lecture which I am taking 5 minutes less in comparison with other lectures. So just as per the usual practice, you are going to turn on your cams and you are going